Hello everyone. My name is Tiyasha Shom. I am pursuing MTech at Tripura University Department of Electronics and Communication Engineering. Today I am here to make you understand about my topic, that is design of an Xnor gate using microring resonator. Well, we all know that optical signal processing is also known as the ultimate aim of photonics, and various attempts have been made to achieve it with each passing day. Researchers from all over the world are working diligently to complete all signals of optical processing on a single chip. The Xnor plays an important role in encoding and decoding techniques, and it can be utilized in parity checking, level processing, pseudo-random number generator, etc. and so on. A microring resonator is usually a round waveguide that is connected with bus waveguides to allow optical fields to be coupled in the ring. The below figure shows that a microring is connected to two bus waveguides and having four ports named such as input, transmit, add and drop. The signal appears at the transmit port when the input signal wavelength and the resonance wavelength of the resonator are different. But when the input wavelength and the resonant wavelength are same, the signal is coupled from the bus waveguide to the ring waveguide and appears at the drop port. The study provides a microring resonator based optimized capable of performing simultaneous Xnor operations. Because optical pumping is employed instead of electrical pumping, this model has superior responsiveness. So, nextly, I am going to explain about the topics, that is basically what is microring resonator, Xnor gate, microring resonator based optical switch operational principle, design of optical Xnor logic gate, simulation and results, future scope and conclusions. First of all, we need to know what is microring resonator. Microring resonator is basically a set of waveguide in which at least one is a closed loop coupled to some sort of light input and output. The concept behind optical ring resonators are the same as those behind whispering galleries, except that they use light and obey the properties behind constructive interference and total internal reflection. When light of the resonant wavelength is passed through the loop from input waveguide, it builds up in intensity over multiple round trips due to constructive interference and is output to the output bus waveguide, which serves as a detector waveguide. Because only a select few wavelengths will be at resonance within the loop, the optical ring resonator functions as a filter. Additionally, two or more ring waveguides can be coupled to each other to form an add or drop optical filter. Xnor gate, also known as the exclusive NOR, is a digital logic gate whose function is the logical complement of the exclusive OR gate or XOR gate. It is equivalent to the logical connective from mathematical logic, also known as the material biconditional. A high output, that is 1, results if and only if both the inputs of the gate are same. But if both the inputs are not the same, the output results as 0. Microring resonator based optical switch operational principle. The microring resonator is made up of a ring resonator and input and output waveguides that are coupled in one direction. As shown in the figure, a fraction of the entering field K1, that is the coupling coefficient between the input waveguide and the ring, is transmitted to the ring with radius r. The constructive interference occurs when the optical path length of a round trip is a multiple of the effective wavelength, and the MRR is therefore on resonance. Periodic fringes emerge at the output ports as a result. Because a fraction K2 coupling coefficient between the ring and the output waveguide of the built-up wave inside the ring is coupled to the drop port that exhibits maximum transmission at resonance. The ring has minimum at resonance in the through port. A logic switch can be built if the resonator is made up of a nonlinear material. These carriers create a temporary blue shift in the microring resonance wavelength by effectively lowering the refractive index of the microring waveguide. The resonant wavelength will change when the refractive index changes, which can be utilized to switch a signal on or off, or to turn the resonator for using it at a given wavelength. So this is the circuit diagram of optical Xnor gate. Here we are using two microring resonators and a phase shifter. The operation of this circuit diagram I will explain you with 4 logics in the next slides. Simulation and result. The simulation of a microring resonator is performed under the premise that there is no optical input in the add drop port and that a continuous optical signal with a wavelength lambda is applied to the input of the microring resonator 1. When the applied voltages are at low and high levels respectively, both MRRs are on resonance and off resonance at the operating wavelength lambda in the Xnor operation mode. Optical logic gates make decisions depending on a mix of digital signals from their inputs. There are 2 inputs and 1 output on most logic gates. Boolean algebra is used to create logic gates. Every terminal is in one of 2 binary states at any one time, false or true. False is equal to 0 and true is equal to 1. The binary output will vary depending on the combination of inputs. A logic gate can be compared to a light switch, with the output being off in one position and on in the other. In integrated circuits, these optical logic gates will be commonly employed in the future. According to the preceding definitions, let us go over the operational premise of the Xnor optical gate in further depth. So, for input 0, 0, when x equals logic 0 and y equals logic 0, when both the input signals x and y are shown off, that is a state in which an optical signal is applied to the input of the first microring resonator MRR1 goes to the throw port of MRR2. Now for input 0, 1, the input signal comes to the drop port of MRR2 when the first input signal x is off and the second input signal y is on, that is when x equals logic 0 and y equals logic 1. Now for input 1, 0, that is when x equals logic 1 and y equals logic 0. The input signal comes to the drop port of MRR2 when the first input signal x is on and the second input signal y is off. Now for input 1, 1, that is when x equals logic 1 and y equals logic 1. When both the input signals, that is x and y, are on, the input signal is sent to MRR2's throw port. For all optical logical operations, the results of all outputs are summarized as zeros and ones. Future scopes. Logic gates will play an essential part in future high-speed optical communication systems such as signal generation, addressing, header recognition, data encoding and encryption because logical functions are assessed at the speed of light. The various reasons that will be in high demand in future are using technology to scale. The development of specialized devices such as switch or an Xnor gate has dominated much of the work in optical logic. We should expect ever quicker, smaller mini optics and more energy efficient gates as optical technology progress. Secondly, computation of multi-channel. A directed logic network with 2 or 3 rows of gates can implement most logic functions. When these rows are viewed as a computer channel, extending the system in 2 or 3 dimensions to construct a multi-channel computing system for highly parallel computation is simple. Thirdly, beyond logic operations. Digital logic was designed in its current form to evaluate logic functions in an optics-friendly manner. This work resulted in a new paradigm for expressing logic operations. However, it lacks a broad computing situation. Future work will focus on overcoming current constraints. Lastly, I would like to conclude that this work proposes a microring resonator with an optical construction that can perform Xnor operation. Using only 2 microring resonators, a unique technique is developed for simultaneously generating the optical Xnor gate operations. The circuit design can be improved further and the output of Xnor operations can be achieved. So, here are the few references from where I have taken guide for my paper. Thank you.